please note, in regards to today's podcast, this interview with Tony Del Genio was done in August 2016, but is now being presented in February 2018. Also, the statements by Tony Del Genio are his personal opinions and do not reflect the positions of any organization he worked with in the past or that he currently works with. Thank you and enjoy. What is your name and what do you do in the field of science?
My name is Tony Del Genio. I work for NASA, and during my career I've been a climate and planetary scientist. And one of the main things that I'm doing now is that I'm trying to do research on the habitability of exoplanets. That is, try to figure out for the types of planets that we've discovered and are going to be discovering in the coming years, orbiting around other stars, which of those planets might have the physical conditions on them that might be suitable for the existence of life. And that mostly means planets that have just the right temperature so that liquid water could exist on the surface, since although there may be life that emerges in other ways, the only life that we know about is life that depends on liquid water. So we look for planets where we think liquid water could exist on the surface, and we use climate models, that is, computer models that we ordinarily use to think about how the Earth is going to change over the 21st century due to the carbon dioxide and other gases that human beings put into it. We use those same types of models to try to simulate conditions on other planets to try to help us understand which types of planets might stand the best chance of being capable of supporting life, so that as NASA makes decisions about which planets to observe in more detail, perhaps we can give them some information that might help them in making that decision. So that's one of the main things I'm doing now. But I also am involved in projects that I've been involved in for a much longer time. I'm on the science team of an existing NASA solar system mission called Cassini, which is in orbit around Saturn. It's been in orbit around Saturn since 2004, and it will be in orbit around Saturn for about another year until the mission is over. And we observe Saturn's atmosphere, and we observe the atmosphere and surface of Saturn's largest moon, Titan, which is a really interesting place too. And then finally, I mentioned the climate models. My day job, so to speak, is that I'm one of the people involved in doing the predictions of future climate change. And my particular expertise and role in that is that I do research on clouds, which reflect sunlight and trap heat and therefore regulate the climate, and storms, because a lot of what you care about in climate change is what happens to things like rainfall patterns and where you'll get droughts, where you'll get floods and things like that.
Mm-hmm. Okay. Now you sort of answered the second question, which is what are some of the current projects you're working on? So do you want to elaborate on anything you've said? That would be great.
I can. Mm-hmm. So one of the things that we're doing, and as a matter of fact, the article is going to come out tomorrow, and you'll probably see a press release. You can even find some stories that some websites have done on it already. Tomorrow, probably you'll see more. But we used our climate model to ask a question about ancient Venus, and that is that Venus is the closest planet to Earth, and it's about the same size as Earth, and scientists assume and anticipate that Venus and Earth formed with very similar inventories of molecules, and therefore constituents. Yet Venus and Earth evolved to be so different. Venus is a place that's terribly hot on the surface. It's got a carbon dioxide atmosphere that's 90 times thicker than our atmosphere is. It's got temperatures on the surface of, I think it's 864 degrees Fahrenheit, which is hot enough to melt lead. And there's virtually no water there to speak of, just a tiny little bit of water vapor in the atmosphere. But decades ago, when NASA sent a mission there, they observed something about the little bit of water vapor that's there that made them think that maybe Venus might have had an ocean billions of years ago. And then what only took about 500 million years to evolve, in other words, to appear.
Mm-hmm.
And so if you could keep a planet with water on it at a reasonable temperature for 2 billion years, then it's certainly not out of the question that life could have evolved, could have appeared and evolved on Venus during that time before it got too hot. So that's a pretty exciting thing. Most of our exploration of the solar system that's been focused on the search for life has focused on Mars, where there's some geologic evidence that liquid water really was there.
Mm-hmm.
It's much harder to come by that evidence on Venus, but we're at least postulating that it's a plausible idea that's worth NASA thinking about trying to send a mission there, and there are several proposed missions to Venus to see if they can learn more about it. So that's one thing we're doing that's immediate, that's coming out right now.
Mm-hmm.
The other thing that we're doing, what I am working on now, the project that I'm involved in, that is the reason that I met you a year ago, the reason I was invited to AwesomeCon,
Mm-hmm.
is that I'm the co-lead of a project called the Nexus for Exoplanet System Science. And the acronym for that is NEXSS, or Nexus. Same as the word Nexus, but spelled differently. And the idea of the Nexus project is that the search for life on other planets is something that traditionally has been the province of astronomers and astrophysicists. And now that we're discovering so many planets, really you need a broader range of expertise. And so you need planetary scientists, you need Earth scientists like me who think about climate. You need heliophysicists, people who study the sun and stars, who understand the different effects that the sun can have on a planet's atmosphere and climate. And you need to get all those people together to think about things. And so I'm involved in that project. I'm actually the leader of one of the teams that's involved in that project, and I'm one of the co-leads of the entire Nexus project. And one of the things that we've been trying to do during the first year to contribute from the perspective of people who have experience studying the Earth is to think about what makes for a really habitable planet. And that is to say, so some people say habitability of a planet is a binary choice. Either a planet can sustain life or it can't.
Mm-hmm.
And that may be true, but if you have a planet that's so hostile to life that you can just have a couple of little niches here and there, well, they might be habitable, but we're never going to figure it out from many light years or parsecs away. So in terms of how NASA's going to search for life, what we're looking for are planets that are more likely not just to have life on them, but to have abundant life that shows itself in signatures that you can see in the planet's atmosphere or on the surface. And so the more life there is on a planet, the easier it might be for us from very far away to tell that life is there. And so what we've been doing is thinking about, well, what would make, from a climate standpoint, what would make a planet more conducive to life versus less conducive to life. And so, temperature is the obvious thing that people have thought about for years. If the temperatures are well below freezing, it doesn't mean that you can't have life there, but it's not going to be as abundant as the surface. Temperatures are too warm, then it's going to be too difficult. It's going to be difficult, in fact, for the planet to even hold on to its water. But once you get in the realm of reasonable temperatures, then the next thing you look for is water. If you actually look at the Earth and where life is abundant, where it's not so abundant, then more often than not, that's determined by where there's lots even the Sahara Desert has life in it, but a lot harder to detect than if you're in the middle of the Amazon rainforest. Okay, so we've been trying to use our climate model to think about what kind of planets would have more of their surface covered by things that are more like the Amazon rainforest, and not so much like the Sahara Desert. And so that's something that we're doing that's exciting. One of the other things that we're doing about exoplanets is if you actually if you think about what kind of a planet you're going to first of all detect, and second be able to begin to characterize, that is, figure out what that planet is like from very far away. Partly it's just a probability issue. So if you ask yourself, if I just found some random planet, where would it be? And the answer is, if you look at all the stars that are out there, and that's the first thing you have to do. You have to find a star, and then you look for a planet orbiting around that star. And if you ask what are the most likely stars out there, well, there are all kinds of stars from very hot to very cool. And our star, the sun, is somewhere in the middle. It's the so-called G star. But if you look at the population of stars, the demographics of stars, you find out that about 75% of the stars that are out there are very cool stars, what are called M stars or M dwarf stars. They're stars that are that to the eye would be a lot more reddish than our sun, which is more yellowish. And those M stars, those red dwarf stars, make up about 75% of all the stars that are out there. And then you can add another piece of information to that, and that is that for a cool star like that, how far would a planet have to be away from such a star to have a chance of having reasonable temperatures, and reasonable is defined in this case as temperatures like we have on Earth, where we know that life can form and thrive. And so if you ask where that happens for a cool star, the answer is very close to the star compared to how far away Earth is from the sun. And then you add a third thing to that and say, well, how do we detect exoplanets right now? And there are 3 or 4 or 5 different ways that scientists find exoplanets. But the most common way, the way that's been responsible for the vast majority of exoplanets that we've discovered, is by something called the transit method. And the idea is simply, if there's a planet orbiting around a star, and the orbit is lined up visually according to the line of sight between Earth and the planet, so that from where we sit on Earth looking at that star, the planet passes in front of the star once during its orbit, just as Mercury and Venus transit across the face of the sun, and we can observe those. In fact, just a few months ago, there was a transit of Mercury across the sun that a lot of people viewed. But if you can find a planet that crosses in front of its star, then that planet blocks out a little bit of the star's light, and that's how you detect the planet, by seeing the starlight dip. And furthermore, you can watch the starlight as it passes through the planet's atmosphere and take a spectrum of that and figure out what gases are in the atmosphere. And so this is one way to not only discover planets, but figure out what their atmospheres are made out of, and that gives us clues as to whether they might be interesting planets from the standpoint of harboring life. And so the NASA is going to be conducting several missions in the coming years. They're going to use that technique to detect those kinds of planets. And so one of the things we're doing is trying to simulate what planets like that would be like. And the interesting thing about those planets is that because they're so close to the sun, the gravitational tides that the star, I should say, raises on those planets keeps the planet what we call tidally locked or synchronously rotating. That is, same face of the planet always faces the star, so that one half of the planet is always daytime and the other half of the planet is always nighttime. Much the way our moon is locked in its orbit around the Earth, so that we always see the same face of the moon, right? But from a habitability and a climate standpoint, those planets are really interesting. It's so different from what we have on Earth. Imagine a planet that's daylight on connection, and I frankly didn't realize this until fairly recently. But there was one episode of Star Trek that I was watching. I just happened to be like randomly flipping the dial one afternoon when I was off. I think I could say it was on a Saturday afternoon. I was just flipping the dial and came across an episode of Star Trek, and I don't remember the name of the episode, but the episode was about them back to her home planet to negotiate a peace between two warring civilizations, and it turned out that the planet was one of these tidally locked planets. It had one side that was all day side, one side that was all night side, and basically there was one civilization that had evolved on the day side, another civilization that had evolved on the night side, and they were always at war with each other. And it turns out that she was the child of one person from each of the two civilizations. So she was the only person who might be able to negotiate a peace. And I was like so surprised because this is an episode from this is like late 1980s Star Trek. And late 1980s, not that many people were speaking about in science about planets around other stars, and this idea of tidally locked planets was I think a relatively new concept. I was very impressed that this had been picked up by a writer for a science fiction show. So you never know about things like that. Anyway, these are the big deal in the science of studying exoplanets, because we know that a large fraction of the stars that we're going to discover in the next few years, a large fraction of the planets around stars that we're going to discover in the next few years are going to be these tidally locked planets. And since we don't have our own experience with them so far, there's a lot of people doing a lot of thinking about what they might be like. So we're trying to think about that from the climate standpoint. And I do other things. I mentioned that I'm part of the Cassini mission to Saturn. One of the things that we're doing now is we watch Saturn's moon Titan, which has methane clouds on it, not water clouds, but methane clouds. And we've been able to watch Titan as it goes from southern summer to northern spring, and now it's approaching northern summer, and we've been able to watch the clouds move around, and we're trying to understand, what Titan seasons basically are like, and how the methane clouds behave, and what that might tell us about its weather in general. And then, as I mentioned earlier, I study climate change on Earth, and right now we're trying to think about storms and how they might change as the climate changes, and how they affect the climate change itself. So that's sort of a tour of all the different research projects I do.
So on Titan, have you found anything very surprising going on?
Yeah. So one of the things I said at AwesomeCon last year, I remember it because I've heard other people say something, other scientists say something similar to this very recently, and that is that we've been, more often than not, we've been surprised as I've been very fortunate to have grown up and had my scientific career during really our first era of the exploration of space, and I try not to forget how privileged I am to have been born and grown up during this particular time in history. But because I've been able to see most of it. It started before I was old enough to have a job doing research, but what we've seen through most of my lifetime as we visited planets for the first time is that more often than not we're surprised by what we find. We try to anticipate what we're going to find, and sometimes we're right. Sometimes we do a good job, but a lot of the time we're not right, and we see things that we did not expect. And with Titan, I remember that before we went there, I really thought that if we were going to see methane, we knew that there was methane on Titan, and we had already known from observations from Earth that there were occasional clouds on Titan. But I had assumed that most of the clouds, and especially clouds with big rain, would be near the equator, because that's the way it is on Earth. Our biggest storms, most frequent storms, even though we get storms in our part of the world, in the United States. The most frequent storms, the most rain happens near the equator. Again, think about the Amazon rainforest or the African jungle, Central African jungles, things like that. And so I thought something similar would happen on Titan. It turns out that really only happens on Titan for a very brief period, right near the beginning of spring, near the vernal equinox. And we were fortunate enough to observe with Cassini a tremendous breakout of storms near the equator back in 2010, 2011.
Mm-hmm.
And it was there for a few weeks, and then it went away. And we haven't seen any storms there in the 6 years before that we were observing Titan, and we haven't seen any more there for the now almost, let's say, 5 years after that. And so it's been actually very different from the Earth, in the sense that what we expected only happens for a very short time near the equinox. And we haven't seen the other equinox, the autumnal equinox, and we won't see that. But I was something similar happened then, but we unfortunately won't get to observe that. What happens instead is that in winter and in summer, whichever hemisphere is in summer, you get a lot of storms forming right at the pole, whichever the summer pole is. So, for example, right now it's the equivalent of, let's say, May, okay, on Titan, and so we're nearing the summer solstice on Titan, and the big clouds are starting to develop near the North Pole on Titan. When we first got to Titan in 2004, it was more like August, or I should say, I'm sorry, it was more like January, really, and the storms were down near the South Pole, and so that's something we don't have on Earth. We don't have huge storms in Antarctica or up at the North Pole on Earth. We never really get those types of storms here, and so that's been something that's very different that I think that really I think all of us did not predict.
Okay. As far as exoplanets, does the term Goldilocks really have applicability still, or it seems like there are too many variables to apply that?
That's a really good question. And so, if you look at what NASA is doing, all right, or what they say they're doing as they design missions and try to figure out how to prioritize which kinds of observations that they're going to do. A lot of people think of that in terms of finding a planet that's just like Earth, and you'll hear different expressions for that. Some people will say another Earth. Some people will say we're looking for an Earth twin, and some people will say we're looking for Earth 2.0. But so you're right. There are so many parameters that can affect what kind of planet you get, and we're really still learning how many different parameters can affect what kind of planet you wind up getting. That you could argue that there might not be another planet just like Earth out there. On the other hand, there are so many stars out there, and the one thing we've learned over the past decade is that planets are extremely common around stars. I mean, we have a very limited ability so far to detect planets, but still a fairly decent fraction of the stars that we've tried to look for planets around, we've found planets, and we've found a number of stars that have multi-planet systems. And this is with very, what I would call very primitive observing techniques compared to the difficulty of the task of seeing all the planets. So we know that we've only seen a small fraction of the planets that are out there, and as we develop more and more powerful and sophisticated observing techniques, we know that we're going to detect a ton more of planets. And so, yeah, there are a lot of variables, a lot of parameters that can change things. So you could very well argue that the odds of finding something very similar to Earth are very small. On the other hand, it seems to us, based on every reasonable estimate we can make, based on the number of planets we've discovered, that there are so many planets out there that Keller and John Armstrong, and they made the point that we're being very biased by looking for planets that are just like Earth, and we're assuming that, just because we know that life does pretty well on planet Earth, that is sort of the ideal planet that we should be looking for. But their point is that we have no idea. We only know of one planet with life so far, and we don't know whether we are an example of the ideal planet for life emerging, or whether we're kind of near the edges of what might make for a habitable planet. And so they suggested, they proposed to the scientific community that we should be thinking about what they referred to as super habitable planets, planets that might be more habitable than the Earth is, and I think that's a good idea. We shouldn't be restricting what we think of. And so if you go about Goldilocks planet, well, maybe Earth isn't the Goldilocks planet. Okay, and when I hear the phrase Earth 2.0, my reaction to that is that, well, in software, 2.0 is supposed to be an improvement over 1.0. And so maybe we should be looking for Earth 2.0, but we shouldn't be looking for a planet that's better for life than the Earth is. And that's actually one of the things that we can at least look at from one angle with our climate model. We can look at a planet that has tropical rainforests over half the planet instead of just a narrow band at the equator, and we figured out how to make a planet like that. And a planet like that might be more conducive to life than our planet is. Another way to make things more conducive to life, perhaps, is to have a larger fraction of the surface be land relative to ocean. So maybe a 50-50 mix might make it more likely that the planet's habitable, we found out. And so there are things like that you can start to think about and imagine what would really be a Goldilocks planet. Mm-hmm. And would it be similar to Earth, or would it be somewhat different? And that's before you even start thinking about really exotic types of planets that are really different from Earth. So some people have tried to think about, whether life could emerge on a planet whose atmosphere was mostly made of hydrogen, molecular hydrogen, H2, instead of nitrogen and oxygen. And we're really only beginning to scratch the surface of thinking about things like that.
Okay. And just to return to Venus quickly, so sort of a two-part question. One, can you have a lander on Venus that could deal with the high temperatures? And two, if you can, would a mission to Venus be easier or more difficult than one to Mars?
So people are trying to think about landers that could survive for longer periods of time, but it's really hard to do, obviously, because of the harsh temperature conditions. And so people are thinking about that. The Soviets managed to land a bunch of probes on Venus's surface, decades ago. And that's, to me, I think we take that for granted a little bit, but that was really an amazing technological feat. Those landers did not last for very long, but they gave us our first pictures of what the surface of Venus looked like. They gave us our first direct measurements of the temperature and pressure at the surface of Venus, and so it was really quite a technological accomplishment, as well as really telling us valuable things about what Venus is like scientifically. I think you're very hard pressed to design something that is going to last on the surface for a long time. Again, people I think are thinking about things like that, but I think it's telling that right now, if you look at the missions that people are actually proposing, right now there
Mhm.
Fortunately, Japan has gone to Venus recently with the Venus Express mission, which is sending back great data now, and that's been very valuable. But anyway, these two missions to Venus are one of them is a probe that's going to drop into Venus's atmosphere, and the main thing it's going to do is take measurements of the atmosphere on the way down, and we'll try to survive on the way down for as long as it can with more sophisticated instrumentation than the types of things that the United States and the Soviet Union were able to do in the 1970s and 1980s. And then the other mission is a mission to be in orbit around Venus and to make measurements that'll get through the clouds and tell us more geologically about Venus's surface and what it's like and what its history may be. So neither of those missions is actually going to attempt to land on the surface and stay there and take measurements on the surface for a long period of time. So it's still a really hard thing to do. And that's one reason why certainly we've spent so much of our resources in NASA's planetary program going to Mars, because Mars is really an easier place to get to. You have to take your opportunities with Mars when it's lined up right in its orbit so that you can do it as quickly and as cheaply as possible.
Mhm.
And the United States has a little bit of a checkered history in successfully getting missions to Mars that get there and land on the surface and actually return data. But fortunately, in the past decade or so, NASA's had pretty good track record with Mars missions. And so I think overall, Mars is definitely an easier place to go to, but increasingly the scientific community is realizing that Venus is, I don't want to say, it's a shame, let's say, that the planet that's really closest to us most of the time is a planet that we know so little about. And we understand we know so little about it because it's a really harsh environment, a really difficult place to send a spacecraft to that actually goes down to the surface. But the other thing that we've realized is that as we begin the search for exoplanets, we realize that a lot of the planets that we're going to discover are planets that may be more like Venus than like the Earth. And so we need to understand better what the differences are between Venus and Earth and how Venus got to be the way it is, so that we have a better chance of understanding what those planets out there around other stars might be like. We're probably going to discover planets that are like Venus more often in the next 5 years than we'll discover planets that are like Earth, just because of the difficulty in detecting a planet like Earth. It's easier to detect a planet like Venus, especially around a cool star, because a planet like that will be very close to the star and something that you can see easily with this transit method. So yeah, Venus is tough, but fortunately it's a planet that is now kind of getting onto the radar screens of the scientific community in a way that it hadn't for many years.
Okay. All right. Now I have a 3-part question. What motivated you to pursue this work as a career? Was there anything in fantasy or science fiction entertainment that inspired your interest in this work? And if so, what was that inspiration?
So the way I got here, I mean, it was sort of an indirect path. And in some ways, you could say I'm doing what I always imagined or wanted to do since I was a little kid. I think it's fair to say that I was always a nerd. I was always interested in science and math, even as a kid, and I was good at it. And so the idea of a scientist became appealing to me early in life. I can still remember the first time I visited the Hayden Planetarium in New York City, and they had a show about planets, and I remember in one of their rooms they had this kind of big mobile kind of hanging from the ceiling with all the planets orbiting around it to give you some kind of a visual perspective of how big the solar system is and how far away planets like Uranus, Neptune, and Pluto, which at that time in my life was still classified as a planet and not a dwarf planet, and that visit to the Hayden Planetarium I don't know if people even remember those anymore.
Oh, I read those. Yeah.
You read those? Okay. I mean, there were like many different series of the Tom Swift books. So I think there were some that like went all the way back to like, I don't know, the 1930s or 1940s or something like that. But I don't think those are the ones that I read. I think I read the ones that in series 2 or 3 or something like that, the ones that were being written in the 1950s. And so,
Mm-hmm.
you know, he was sort of a role model. I mean, he was somebody who was inventing things, and eventually, I mean, at the beginning, he was just inventing things. But then he was like going to other planets, and he started that as a kid, and like this adult running this corporation and doing stuff, and then he got his descendants that are doing it for him. But anyway, I was very excited by those books. The first kind of, you know, let's say, you know, serious science fiction novel that I remember reading, I can't guarantee it was the first one I remember reading, was Have a Spacesuit Will Travel by Robert Heinlein. And again, you know, this idea, not that one is as pleasant as some of the Tom Swift books are, because he winds up being kidnapped and taken to the moon, but still, but this idea of getting a spacesuit and you know, being able to travel in space, something about that just really fascinated me. And for most of my childhood, you know, after those experiences, I wanted to be a scientist, and I wanted to study the planets. For a brief period of time, I decided I would rather be a Major League Baseball player, and then I got into Little League. In my first season in Little League, I got 2 hits the entire season, and quickly became obvious that being a professional athlete was not something that I was cut out for. That eliminated my other job possibility. And science just sort of became the thing I focused on after that.
Mm-hmm.
And actually, by the time I got to college, I went into a program of aerospace engineering, where, you know, which is basically what you major in if you want to, you know, build rockets and things like that. And it turns out after I got to college and started to learn more about the field, I decided I wasn't really that interested in it, but I was still interested in space, and I managed to find a professor who was a planetary astronomer himself, who sort of convinced me that, well, you can do this for a career. You can actually get paid to study the planets, and that convinced me really to pursue that during my career. And then I got to graduate school, and actually at that time I was planning on I was planning on doing research on planets, but I was gonna do research on the interiors of planets. Okay, what's going on inside the planets, beneath the planet's solid surface. You know, from the surface of the planet down to the core. That aspect of planets. And at the end of my first year in graduate school, every first year graduate student had to take what they called the comprehensive exam, which is this 2-day written exam, which tested you on all of the areas of science that the department covered, which we had been taking courses about in our first year. So we were supposedly prepared to answer questions on any aspect of planetary science. And so I took that exam at the end of my first year, and it turns out the section of the exam on the interiors of planets happened to be on aspects of the interiors of the planets that I learned that day I really just did not understand very well, and I completely bombed that part of the exam. Meanwhile, another part of the exam, which was about planetary atmospheres, I did great on that part of the exam. So after you take the exam and they grade the exam, they don't just give you your exam booklets back. They sit down and have a conversation with you. And so my advisor sat down with me and reviewed the results and said, "So, have you ever thought of doing planetary atmospheres instead of planetary interiors?" And I couldn't argue with the evidence, and the idea of planetary atmospheres seemed like a pretty interesting thing, and that's how I wound up actually getting into that field. And fortunately for me, the place where I work now, the Goddard Institute for Space Studies in New York, had an instrument that was going to launch on board a mission called Pioneer Venus that was was going to get to Venus in late 1978, just about the time that I was getting my PhD, and the director of GISS, Jim Hansen, who's very famous for his work on Earth climate change, was looking for postdocs to come work on the Pioneer Venus mission, and so that's how I came to work at the place that I am now. And that sort of kind of sequence of events meant that I learned something about planetary atmospheres. I learned something about climate change, and in that way, I managed to sort of develop a career in both fields. And then as far as exoplanets go, that's really only happened in the last few years. I've been watching with excitement the emergence of this field, which as a young scientist I would have never imagined I would see in my lifetime, and as people started discovering not just planets around other stars, but smaller and smaller planets, including planets that might be Earth-size or close to Earth-size, even though those are still a distinct minority of the planets that we've discovered so far, because they're so hard to see. It's a lot easier to see the big planets that are Jupiter-size or bigger. Much harder to see small planets like the Earth, like Earth-size. That became more and more exciting, and I saw that people were starting to ask questions about those planets beyond just things that astronomers could do. People are still starting to ask, is this a planet that might have a reasonable surface temperature on it so that you could have liquid water and things like that? And as a combination climate scientist and planetary atmospheric scientist, that was right up my alley, because I'm used to thinking about, what things are going to cause the Earth's temperature to change, and I'm used to thinking about how do you translate that knowledge to other planets in our solar system. It was very easy for me to start thinking about stuff like that. And it turned out that there were a few people at my place and at our parent institution, the Goddard Space Flight Center in Maryland, who were already thinking about using our Earth climate model to try to simulate exoplanets. And they got me involved in that, and I became a part of their team, and eventually I became the lead of that team for the proposal that we wrote to NASA. And here I am a couple of years later, and now exoplanets is a pretty major part of what I spend my week doing every week.
Okay. Just to go back to sci-fi quickly, did you have a superpower or technological device that you wanted to have or use when younger?
I can't say that I did. I was a big fan of Superman growing up, and I never imagined myself though having his superpowers. I was kind of a scrawny kid. I never saw myself in the cape and tights the way he was, but I can't say that I ever imagined myself as him.
Okay. All right. Is there anything in science fiction entertainment that you'd like to see more of to generate interest in your field or other science fields?
Yeah, in most of the science fiction that I watch or read about, what you don't learn about is, or hear much about, is how do you figure out whether a planet is inhabited or not? Somehow they know when they go visit some planet that either this is a planet that supposedly is not inhabited or it's a planet that is inhabited. They know something about the civilization that's on it or whatever, but they never talk about how you learn that there's life on another planet. And that's really what we're doing in the real world today in the science of exoplanets. We're trying to figure out not only what kinds of planets might be habitable, might have a climate and surface conditions that are conducive to life. Something is not, as going back to Goldilocks, not too hot, not too cold, just right. But a planet that not just is habitable. That's what I just described as habitable, with just the right temperature, so that you could have liquid water on the surface, which is a necessary ingredient for the only kind of life that we know. That's a habitable planet. But just because a planet is habitable doesn't mean that it's inhabited, that it actually has life there.
You're right.
And so that they might interpret as being communications from an extraterrestrial intelligent civilization. And as that's one way to do it, but another way to do it is to look for ways in which life has affected the planet and changed the planet. And life does change a planet. And that science is called biosignatures. And so people have been thinking, and this is something that actually Carl Sagan wrote about a number of times many years ago. And in fact, in 1993, he did an interesting little experiment. NASA was sending a spacecraft called Galileo to the planet Jupiter, and to basically, there's a cost and a technological challenge to getting something to Jupiter. And so one thing, and many years ago, they imagined that the space shuttle was going to be used to launch spacecraft to other planets, and then after the Challenger disaster, they gave up on things like that. But meanwhile, they had also given up on the earlier technologies like the Saturn rocket that used to launch big things into space. And so people had to start to come up with creative ideas for how to get spacecraft to other planets. And so they came up with this idea of a gravity assist, that if you were going to go to some other planet, you'd launch your spacecraft so that it flew by another planet and flew very close to the planet, not so close that it would get captured by the gravitational field of the planet, but just close enough so that it would be deflected and sort of taken around the planet and thrown out the way a slingshot would throw out something, gaining momentum from and energy from the planet as it went. And by doing that gravity type of thing, you could get to a planet more easily with less fuel than if you just tried to get there directly. And so NASA became very fond of doing these gravity assist mission trajectories that would take your spacecraft past other planets before it would get to the planet that its eventual destination was. And so Galileo was launched, and first it went to Venus and got a gravity assist from Venus, and then they sent Galileo back to Earth and had it fly by Earth at close distance to get a gravity assist from the Earth. And so while Galileo was flying by Earth, they turned the instruments on and they took some data. All right? And so Carl Sagan wrote this paper in 1993 along with a few of his colleagues, basically asking the question, if you didn't know that there was life on Earth, how could you tell that there was? Right? Interesting question. And he published this, I think, in Science magazine. And so they asked, well, what are the signs of life on Earth that we could detect from space? And so the obvious thing, for example, is oxygen. Okay, Earth started out without oxygen. Earth early in its history probably had a lot of nitrogen in its atmosphere. It might have had carbon dioxide, might have had methane, but it didn't have any oxygen at first. Might have even had some hydrogen early on in its history. And it took a good 500 million years for photosynthesis as we think of it today, photosynthesis that uses carbon dioxide, takes carbon dioxide out of the atmosphere and puts oxygen into the atmosphere. There's about 500 million years at least, if not longer, before that started to occur. And so our atmosphere now, which is like 21% oxygen, is very different from the way our atmosphere was at the beginning. And so if you were an alien civilization looking at the Earth and saw all of this oxygen in the atmosphere, you would say, that's kind of interesting. That's something that we don't expect to see. And so that would be an example of a biosignature. And there are other things that you can imagine. A lot of the methane that's in our atmosphere is due to life. And in fact, the combination of having oxygen and methane together in the atmosphere might be a sign of life, because if you just take a chamber and put oxygen and methane in there together, you're going to get a chemical reaction that will destroy the methane. And so the fact that the methane is there tells you there must be something that's putting the methane into the atmosphere, and life is what's putting the methane into the atmosphere. People do it, but also it happens in rice paddies and bogs and swamps and places like that, and so on. So they wrote a whole paper about how do you actually figure out that the planet you're looking at has life? somehow in science fiction, as we go into the future, people made reference to that a little bit, and how they know that they're going to an inhabited planet. I think that would be great, because it would be a way to link that to what's actually going on in the scientific community, the real way that we're trying to do it right now, where we're really trying for the first time to figure these things out.
So, just to touch on the biosignatures, do you think life, either ranging from cellular, single cell to to human beings, do you think the biosignatures are more prominent on the surface, like fauna or buildings or whatever, terraforming, versus atmospheric biosignatures?
Yeah, that's a great question. The atmospheric biosignatures are, and there's a lot of discussion about this, by the way. So I would say that I can't give you a definitive answer, but I mean, most people think that the atmospheric biosignatures are a lot more easily detectable on an inhabited planet, and it's the only place you'll have a biosignature, because of one thing, and that's the love of my research life, which is clouds. So in my research life, clouds have paid my salary for about 3 decades now, and I love them. They're so interesting scientifically. But to exoplanet people, clouds are a dirty word, because clouds get in the way. And they get in the way of atmospheric biosignatures, and they get in the way of especially surface biosignatures. So on our planet, fortunately our planet's not completely covered by clouds. We're only about 60-70% covered by clouds, and so there are enough clear places where you can see down to the surface, and you might have the chance of seeing surface biosignatures. But it's a challenge because of the clouds to get enough of a signal from the surface that you could really differentiate life. And one of basically the main way you would differentiate biological life, like vegetation or something like that, is that if you observe the Earth at different wavelengths, it turns out that vegetation reflects a lot of sunlight at wavelengths just longer than our eyes are sensitive to in the near infrared, but it absorbs a lot of sunlight at wavelengths that our eyes are sensitive to, which is why plants have colors, like especially green. They're absorbing other visible wavelengths, that they don't absorb quite as much green light. So plants look green. So we try to look for that difference between the light between the wavelengths that our eyes are sensitive to and the wavelengths that our eyes are not sensitive to, as a sign of vegetation. And in fact, NASA uses that in Earth orbiting satellites to monitor the health of vegetation. They can actually detect from space when there's an area on the globe where vegetation is dying or is under stress because of drought conditions and things like that, by doing these kinds of measurements. But it's one thing to do that in Earth orbit, looking down at the Earth, where you're only hundreds of miles away from the surface. Another thing to do that from 30 to 50 light years away. And so people are thinking about it, and they're trying to do it. One thing that people have done is to try to take. So there have been satellites that have looked back at Earth and taken images of Earth from relatively far away, so that you can see kind of the whole disk of the Earth. And what people have done is they've taken those images and they've basically averaged over the entire image to make basically 1 pixel. So, which is basically what you're going to see when we eventually take images of Earth-sized exoplanets. It's going to be 1 pixel that's going to represent the whole planet. Mm-hmm. And they've asked, is there a way that you could figure out what the Earth is like by just looking at this 1 pixel? And the answer is, yeah, there are ways you can do it. It's hard, and they're still working on the best ways to do it. But for example, if you can take many images over a long time period, then you can figure out that Earth rotates about once every 24 hours. If you take images at different wavelengths over the visible part of the spectrum and into the near infrared part of the spectrum, you can figure out that it has an atmosphere. You can figure out where that it's got clouds. You can big area of research in the field right now is to try to refine those techniques to see whether they'll work for exoplanets. As far as detecting the signs of an intelligent civilization, there is one thing. So it will be hard to detect that on the planet itself, I think. It's more likely that you could detect it if the planet was had such an advanced civilization that it had gotten to the point of actually modifying its star. So I don't know if you've heard of the concept of a Dyson sphere.
Yes.
The idea that you might just kind of like regulate the amount of starlight by just building a big structure around it, and so, I mean, that's something that's part of science fiction or science imagination, let's say, about the long-term future. But a funny thing happened a year or two ago. These astronomers at Yale University discovered a star that was behaving weirdly. Let's put it that way. Okay, a lot of people are looking for planets around other stars by watching the starlight get blocked as the planet passes in front of the star. And if you detect something like that, although it's a technological challenge to do it, but basically if you have to do it over and over and over again, so that you average over all the transits and you can beat down the noise and actually see the signal. But when you do that, then it's a very regular thing. You can see the starlight dip, and then a few hours later you see the starlight go back up again, whatever, depending on what the orbital period of the planet is. And it's very regular, and it looks very similar kind of going in as it does going out. But they discovered the star that was showing very irregular fluctuations in its starlight. And they tried to come up with like a variety of explanations for why this was happening. And one of the things that they actually considered was the possibility that there was some kind of an alien megastructure, that had been built around the star to kind of regulate the flow of starlight and toward the planets in the system. And the reason, and ordinarily scientists would be very, let's say, very reluctant to even mention such a thing, but they felt they had to mention it in the paper that they published because they had half a dozen other theories that don't involve life or anything like that, that would explain the behavior that they were seeing. And one by one, they've ruled out all those other theories. and so they felt that they didn't want to really believe it themselves, but they sort of felt they had to mention this other possibility, as unlikely as it might be. And the funny thing about this star is that they haven't figured it out yet. If you Google Tabby's star, Tabby ''S star, then I'm sure it'll be easy to find. And Tabby's star is named after a postdoc named Tabitha Boyashi, who was part of the group that discovered this star. And she's sort of like taken this on as a personal quest. And actually, she's doing trying to do crowdsource funding to try to get money to do more observations of this star, so that they can start to figure out what it is. But regardless of what Tabby's star actually turns out to be, it does raise the question of whether you might actually detect an intelligent civilization on a planet orbiting another star by noticing strange behavior of the star itself. So nothing about the planet, but the star, which is a much bigger target than the planet is. I mean, that's the thing about the star. If you notice something weird about the star that makes you think something is going on, then you're a lot better off, because it's so much easier to observe the star than any planet around the star. So, so that's the first time that anyone has really have been looking for radio signals that would be emitted by planets, and we've known that for the past 100 years, Earth has been inadvertently emitting radio signals into space just because of the advent of radio and television.
Mm-hmm.
Right? Once the radio and TV eras came, although the goal was to send those things to other places with antennas that would receive them and be able to display them on a monitor or through a loudspeaker or whatever. Those radio waves, a lot of them are escaping into space and are traveling unimpeded through large distances. And so any intelligent civilization within about 100 light years of the Earth, since radio waves travel at the speed of light, any intelligent civilization within about 100 light years of Earth could conceivably have received some of our early radio and television transmissions. And actually, this is something that Carl Sagan speculated about many, many decades ago, about half a century ago, in a book that he co-wrote with another scientist. He imagined that the way that life on Earth would be discovered by an intelligent civilization elsewhere would be by the intercepting the broadcast of some TV show like the Beverly Hillbillies. Then he wondered what they would think of. That was the first sign of life that they had. Nonetheless, radio signals are still, probably the most obvious way to figure out that there might be some kind of intelligent civilization present. The other way that you could do it, if you could observe for a long time, if you think about our planet, if there's an intelligent civilization somewhere that's monitoring our planet, what might they see happening to our planet over a period of about 100 years? And going back to the biosignature thing, if they knew enough about our planet, sort of to know, what our orbit around the sun is and what the length of our day is, and realize what sort of all of the astronomical parameters are about our planet, and they were monitoring the composition of our atmosphere accurately enough, then they would notice that since about 1850, the concentration of carbon dioxide in our atmosphere has gone way up, and by the middle of this century, it will have become about twice as large as it was in the pre-industrial era. And so if you saw an upward trend like that over several centuries in a gas like carbon dioxide that's a natural byproduct of fossil fuel combustion, or if you saw something similar happening to methane or another gas like nitrous oxide or even chlorofluorocarbons, let's say, which is a totally human-produced gas that you don't have until you have technology, then you might detect that there's an intelligent civilization there. Of course, the longer you watch the concentrations of those things rise without leveling out, you might start to wonder just how intelligent the civilization was, since you conclude that they're doing something to their climate that's making their planet less habitable all the time. But you conclude that at least the technological civilization has developed.
Mm-hmm. Okay. Are there any science fiction or fantasy books, movies, or television shows that you might recommend, and why would you recommend them?
Well, I'm biased. Okay, I have my favorite shows, but I'm a huge fan of Doctor Who, and there are many reasons why I love Doctor Who. The first reason I love it and would recommend it is that the show itself and the Doctor himself are so aspirational. The Doctor loves the universe. He loves planet Earth, but he loves the universe, and he loves the wonder excited about every place that he goes. And I really think that kind of excitement about life and that awe about nature is something that's so important to nurture in our young people and to maintain as adults. It's actually very easy for children to be excited and to be aspirational, and then they get older, or we get older, and then all of a sudden we lose that, and we become more kind of whatever, and the field that I'm privileged to be working in right now is as exciting and inspirational as you can get, and I think that's one of the things that science fiction does for us in general that is so important in our lives that we should really never try to use that. The other thing I love about Doctor Who is that it actually tries to teach people about history and science in an interesting setting. I mean, if you actually watch Doctor Who a lot, you learn a lot of things about Earth's past history. One of the even the older episodes of Doctor Who that go back to the 1960s and 1970s. There was one episode of Doctor Who that was around 1980 with Tom Baker, the fourth Doctor in it, where they actually postulate how life got started on Earth billions of years ago. They actually made a mistake in the show and said it was 500 million years ago, when actually it was more like 3 billion, 500 billion years ago. But they actually showed people a view of the Earth as it was during what geologists call the Archean period, 3-4 billion years ago, and confronted the question of how did life get started on Earth. And of course, in this episode, life got started by aliens that had landed on Earth, and this alien spacecraft tries to take off and essentially explodes, and that provides the electrical spark that produces the chemical reactions in the organic gunk that's sitting on the surface of the Earth that gets life started. Well, I don't know if that's how life actually got started on Earth. There was a particular take on that, which is fine. But just this idea that they would actually try to communicate that idea about how life got started, and even in the new era, early on in the new series with Chris Eccleston, the Ninth Doctor, he takes Rose, I guess 5 billion years into the future, to watch the end of the Earth when the sun begins to go into its red giant phase. And again, it's and it's all in the interest of entertainment. But if you're not inclined to be thinking about the fate of the Earth, it's very educational to realize that the Earth is not going to be like this forever. That we've got a few billion years left. Eventually, the Earth is going to be gone too, and tells you about the lifetime of stars and things like that. And so it really does a nice job, I feel like, of doing that. And I would argue that Doctor Who tries to teach people moral lessons as well, because he's trying to do the right thing all the time, and sometimes he struggles with doing the right thing. And so some of the shows are about the consequences of him trying to kind of take charge too much, do too much. And there are actually a number of episodes of Doctor Who like that. There's a great episode with David Tennant called "The Waters of Mars," where he comes across the first human civilization to colonize Mars, but things go badly wrong, and they're about to all die, and he gets them into the TARDIS, leaves some of them, and takes them back to Earth, and the people who are saved actually resent, at least several of them resent being saved, because they think that that's not right, that's not what's supposed to happen. And that's a great episode of Doctor Who. And you see the same thing. You see the same thing a lot during the Matt Smith episodes, and recently during the Peter Capaldi episodes of that. So it's really Doctor Who. Really, I think is a great show. It has a lot of angles to it. As far as books go, I was thinking about this, and I was trying to think of one book that I think it would really do it, and the one that I thought of was Stranger of a Strange Land, and I'll tell you why. I mean, it's kind of a weird book to choose for this, but first of all, I guess I wouldn't more adult things about that book. First of all, it's a historically important book. I mean, arguably, Stranger in a Strange Land is sort of like the first really famous science fiction book.
Mm-hmm.
And so, just from that standpoint alone, if and it's not that there were no science fiction books written before then, but really that book got science fiction on the map, I think. And so in that sense, I think it's an important place to start for people who are serious about reading science fiction. But the other thing about it is that it raises all these questions. It's a very provocative book.
Mm-hmm.
And it's got lessons in it about religion, and
Mm-hmm.
and I don't want to get into religious discussions, and everybody has their own take on that. But I think if you read that book with an open mind, it will make you think about either a religion that you belong to, or if you don't belong to a religion, the state of the world with various religions in it, and think about how all of that came to be, and how one might usefully think about religion and its place in society in our lives, and how you might think about it in ways that aren't so useful. Because really, if you read that book, it certainly does not portray religion in general in a very positive light. So you can agree with that or disagree with it. That's not the point. The point is to think about the role that religion does play and might play, whether you are part of a religion or not part of a religion, want to be part of one, don't want to be part of one. But the fact is, religion is a part of our society today, and it does affect many things that happen in our society. And that book is a great way to kind of think about that from different angles. The other part of it, and the main lesson, right, is I would say, even if you don't think about it at that larger level, you think about the protagonist of that book, Michael Smith, and he's a human, but he's raised in a different society, and then he comes to Earth, and he just doesn't understand so many of the things about the way we behave, even though he's a human himself.
Mm-hmm.
And I think that's a great lesson, regardless of what you think of religion or anything like that. This idea that we have so much trouble understanding different cultures that have different traditions and different values. And I really think that that's a pretty important thing for us in our society today, because I think a lot of the problems that we have in our world today can be traced to that we don't understand other cultures, they don't understand us, and we look at the world in different ways, and we're all human beings, but we have a different path to how we got to where we are, and that has caused us to have different values. Well, he's sort of the ultimate example of that. He's a human being, and he's raised by Martians instead of human beings, and so he grows up with a completely different set of values, and it just makes that very clear. Even in our own country today, all of the political arguments that we have, or all of the disagreements between different parts of the country about how they look at things and what their priorities are and what they see as the imperative for our country going forward as we go to the elections. At some point, you have to realize that all of this somehow comes from just our different life experiences and what we've been exposed to growing up, and that you have to be aware that at some level we're all human beings. And I think this book is a good way to start thinking about those things. And from a scientific standpoint, I think about something that we think about in science a lot, what I guess psychologists call the nature versus nurture question, right? And they sometimes they wonder about if you have twins who are separated at birth and grow up in different families, how similar and how different do they wind up being, and how much of it is genetic, and how much of it is in the environment in which they're raised. Well, I don't think about that much in my career, notion that uh, that that if we can observe an exoplanet and figure out that it's has just the right properties and is in just the right place relative to just the right star, then it's going to be something like Earth. All right, but Venus, which is the closest planet to us in our solar system and formed near us with what we think are probably similar original ingredients, molecules, as the Earth did, just closer to the Sun, wound up being very different. Now, most of us interpret that as being because Venus is closer to the Sun, and we assume that caused the different evolutionary paths of Earth and Venus.
Mm-hmm.
But there are some scientists who are beginning to say, maybe, but maybe not. There's this question of whether starting from a particular initial condition, that's what we call it in science, but particular conditions at the beginning of when a planet is formed, if something slightly different had occurred, might our planet have evolved very differently? So, for example, our planet's evolution was greatly affected by the relatively accidental phenomenon that some decent-sized other planets came in and collided with it very early in the Earth's history and knocked off a bunch of the early forming Earth and threw it into space, and that stuff eventually coalesced and became what today we know as the Moon.
Mm-hmm.
Well, that was a huge impact on the composition of our planet. It was a huge impact on how fast our planet rotates, on the tides that we have, and so on and so forth. And Venus didn't have that, apparently. Venus might have had another close encounter with a planet. We don't know. But it certainly didn't have anything that formed the Moon. What if the planet that collided with Earth and formed our Moon, what if that had not happened? How might the Earth have evolved differently than it actually did? And so some people are at least raising the question of how much of what we see in the planet is inherent to what they start with, and how much is an accident of things that happened along the way, and whether even our own planet might have evolved completely differently if certain things had occurred differently in its past. And again, that's a lesson that a stranger in a strange land raises. It's just an accident that Dalton Michael Smith winds up being raised the way he starts out with an Earth family, but then winds up in the end being raised by the Martians. And he comes to the Earth, and some things are similar and familiar to him, and some things are different. And his set of values are different because he's been raised in this different environment. So clearly there's a combination of nature versus nurture in the biological psychology stuff going on in that book. But it's got so many parallels in other areas of science, including the one that I'm involved in right now.
Okay.
And I think the general lesson that I would say that comes out of my answer to your question is that anything that makes you think about something that you haven't thought about before, or something that you haven't considered seriously before, is valuable. And that's, I think, the true test of a great piece of science fiction, whether it's a movie, a TV show, a book. Does it make you think? And if it makes you think, it's really serving some larger purpose just beyond the entertainment.
Yeah. Okay. Is there anything you've seen presented in science fiction that you felt could have been presented in a more scientifically accurate way, and what was that?
Yeah, I think you can come up with plenty of examples. I'll give you two, and the two examples are different in important ways. And the question is it something that could have easily been avoided, or is it something that was central to the plot and therefore really could not have been avoided? Because people who are creating fiction have to have artistic license to do things, and so you will concede things that aren't scientifically accurate for good reasons, but not for mistakes. So I mentioned earlier that actually checked and gotten the right number for. Of course, it was a lot harder to check things in those days, and I would try to remind myself about what things were like before the internet and after the internet. It's a lot easier now to do fact checking than it was back then. But the one example that I always notice when I'm watching science fiction is when people go to another planet. The planet always looks unrealistic to me as a scientist, and especially as a scientist who studies clouds. If you look at a satellite image of the Earth and a satellite image of Jupiter, for example, they're very different looking, but they're not random. There's some level of randomness, but they're like organized patterns of the clouds,
Mm-hmm.
and you can see very easily on the Earth where we have these big swirly cloud patterns in the mid latitudes of both hemispheres that are the results of our mid latitude low and high pressure centers and our warming cold fronts and things like that. And
Mm-hmm.
Jupiter doesn't have things that look like that, but it has these bands that go around the planet, alternating bright and dark and very kind of like horizontally oriented. And Saturn is the same way, pretty much, although without as much in a less dramatic way than Jupiter is. And those things aren't random. They have to do with how real planets behave and what their properties are. But when I watch shows on TV, they usually have, I guess there's some graphic artist that has created a planet and just decided kind of like, just like if you were just like throwing stuff up against the wall, they just kind of like try to put some random distribution of clouds on the planet. And you really don't have to do that. You really could imagine some kind of a planet that has an appearance that actually resembles something that you might see or might imagine that you could see it. And with a little more work, they could be a little bit more creative and scientifically accurate in doing that. And I thought that's something that would be easy for them to do that I only rarely see. But maybe a more interesting example is something where people have done something that's unrealistic that is justifiable because of the plot. And so if I think about the movie Interstellar,
Mm-hmm.
which is a really interesting movie. So my colleague down at Goddard, Jeremy Schnittman, who is an astrophysicist and somebody who has studied black holes for a living,
Mm-hmm.
he actually has a seminar that he's given in many different places, and you can find it on YouTube if you just Google Jeremy Schnittman, Schnittman, Interstellar. You'll find eventually a YouTube video of a talk he gave at the Library of Congress, where he goes through the movie and basically explains why Miller's planet couldn't have been a habitable planet.
Yeah.
All right, and there are actually a long list of reasons. One thing I will say about Interstellar is that the imagery they give you of the black hole itself and what it looks like is extremely realistic. They did an absolutely great job of portraying what Gargantua would look like, the debris disk around it, the glowing debris disk around it, and the part behind the black hole that you can see because gravitation deflects the light and sends it up so that you can actually see it. It looks like it's above the star rather than behind the star. All of that is extremely, extremely realistic. When I was down to visit him once, he showed me a simulation that he did of a black hole, and he showed me what the visualization would look like, and it looks exactly like the thing in the movie. They really did a great job on that. But the planet itself would have been that close to the black hole would have been fried for, I think he gives 9 different reasons for why it would have been fried. And if it wasn't the tremendous heat coming from the accretion disk, it would be the neutrinos that are coming out of the area just outside the black hole's event horizon. And so you couldn't have had something like Miller's planet that you would stand the least chance of there being life on. But if you ask why the movie puts Miller's planet where it does, close to the black hole, there's a big reason for that, and the reason is that they wanted to take advantage of time dilation. And I'm not a relativistic astrophysicist. Okay, so I know only a little bit more about time dilation than a layperson would. But but the idea is that the closer you are to this massive object, the more time is dilated, and so it's crucial to the plot that the travelers who are going there to these planets, trying to figure out which one their colleague is on, and which one might be habitable. They're going there. They're doing something over, I guess, a matter of hours or something like that. It winds up, being a huge amount of time that is lost due to the time dilation. So that's something that you can, and in fact, a very famous astrophysicist named Thorne was an advisor to the people making that movie, and he actually wrote a whole book about the science of interstellar and why you're seeing what you do. And I guess in that book he explains that he pointed out to the director or producer, I don't remember which, Christopher Nolan, that you really couldn't have a planet that close, but they needed to have the time dilation,
right,
because of the plot and what they were trying to accomplish with the plot. So they said, no, that's non-negotiable. We have to put Miller's planet close to the black hole. So in a situation like that, you have to say, fine, this is science fiction. Put the planet where you want to put it.
Yeah.
And so I think you really have to differentiate those things. It's very hard to get everything right in the movie. That Interstellar gets a lot of stuff right. If you read, and partially it's because they had an astrophysicist advising them, I'm sure. But in that sense, it's a great thing. By the way, although they don't talk about this too much, it's a movie that has as its kind of starting as its motivation the fact that humans are ruining the earth and making it a relatively desolate place where you can't grow crops anymore and things like that. And while that's a little bit extreme in its portrayal of the earth, still it's pointing people to something real that's kind of happening now and in our future on a more limited extent than the movie portrays it. But it's raising an important question about that too.
Okay. So, what sort of additional science education outreach might you want to see in general or at science fiction or comic book conventions?
So, my first reaction to that was, I have to tell you that the panel that I met you at last year at AwesomeCon was the first time I had done something like that, and I was a little skeptical of it. And the reason I was a little skeptical of it was, first of all, because they put us on Saturday morning at 10 o'clock, and I think the convention started on Friday, and I'm saying to myself, Saturday morning at 10 o'clock, these people have been at this convention all Friday, they've probably gone out and partied on Friday night, they're probably sleeping in on Saturday, figuring I'll go to AwesomeCon later in the day, because all there is stuff like this science panel at 10 o'clock in the morning, and who wants to go?
Yeah.
Who wants to go to something like that? And I was just so thrilled when I got there to see that I agree that we didn't have the big rooms that the TV and movie stars have. We had a modest size room, but I was thrilled to see that on Saturday morning at 10 o'clock that room was filled, and by the time we were finished, there were people there. They were standing on the sides and in the back of the room, and I was so gratified that people would think that it was worth them getting up that early in the morning and choosing to do that when there were other things going on at the same time, but actually choosing to come to this thing where there was actually going to be science in addition to science fiction discussed. So I'm really pleased that AwesomeCon would do that. And by the way, there's a magazine called Physics Today, which is, I guess, the kind of news journal of the American Physical Society. And there was actually somebody from there, who's now I think their editor, who was at AwesomeCon and actually wrote an article about the panel that I was on that appeared in the online version of Physics Today. And the point of his article I think he says in the first line of his story to the Physics Today audience, which is basically scientists, the first thing he says is I'm happy to report that science was alive and well at AwesomeCon. And so he was impressed too that there were these things happening. There was another convention called Escape Velocity that happened like the first week in July this year,
Yep.
and I was invited to be on a panel at that one. Actually, I was invited to be on 2 different panels at that one, but that weekend I just couldn't make it, so I wasn't able to go. So, I think this is happening at these conventions, and I personally am thrilled. And the other thing that I was thrilled about is that we got great questions from the audience, and we got some what I thought were excellent questions from people, and so I was really appreciative that people were that interested, that engaged in what this discussion was going to be, and I really didn't know what I was going to get when I first went there, and after I did it, I was so glad that I did that. But I'd love to do another one in the future if I can. So that's the first thing to say. I think things are in good shape in that regard. So if there's other stuff that I would like to see us tackle in scientific outreach, and it kind of goes back to the stuff that we were talking about earlier. Obviously, what excites people the most is the idea of traveling to other stellar systems.
Mm-hmm.
Right? How exciting would that be to go to another planet? And that's the premise of so much of science fiction is going to another planet in another stellar system.
Mm-hmm.
But it's a really difficult thing to do because of the distances. And so we absolutely should be thinking about ways that we should do it, and that was a large part of what the panel discussion was about, ways that you might actually get to another planet. But over the next few decades, the odds are that that's not going to happen. In the meantime, though, we've entered a very serious phase of trying from a long distance away to at least figure some things out about what other planets might be like.
Mm-hmm.
And the possibility is there that we might actually detect life on another planet in our lifetimes. And in your lifetime, I would say, pretty decent chance. In my lifetime, I'm older, but even in my lifetime, it might happen. Okay,
Mm-hmm.
NASA, I think, is fairly optimistic that we might detect life elsewhere over the coming decades. And you can't put an exact number on it, but NASA's taking this seriously because they think that we can succeed at doing this. And this is something that could very well happen in our human lifetimes, even though we won't be able on that time scale to actually go to another planet. And so it would be, I think it would be great if that aspect of the search for life, which admittedly is less exciting than actually going there, but is something that is really happening. And so it's exciting because it is really happening now. We're really working on it and trying to make it really happen. And so it's exciting in a different way, even though viscerally it's not as exciting as if you actually went to another planet. So that's one thing that I would love to see happen more in science education outreach, or even in science fiction or comic book conventions. The other thing is something that I've thought about a little bit, and admittedly it is not my expertise, but imagine that we did discover life.
Mm-hmm.
However we did it, okay, whether it was a message that we intercepted from an intelligent civilization, whether it was just discovering oxygen and methane on a planet that we could figure out had liquid water on its surface, or whether we actually saw signs of vegetation on the surface of some planet that we think we discovered. However you imagine us doing it, right now at this moment in history, we only know of one planet that has life. And what would happen to our world, our society, if discover life elsewhere. I have to think that that would be one of the largest moments in human history. And it's not just because I'm trying to play a small part in this right now, but I think before I ever got involved, it was something that I thought about. And science fiction writers have thought about this in the past, what the ramifications are of actually finding out that there's life on other planets. But I think there's a lot of room for interesting discussion about how people would react if they were actually confronted with evidence that there was life someplace else. I think that could be a good thing. It could be a bad thing, depending on your outlook, depending on religious beliefs, depending on your own view of life in general. But I think it would be an interesting and complicated thing for our society to digest. And so more science fiction that explores the impact on us of finding out that there is life out there, and I think it's very fertile ground for the type of panel discussions that now are taking place a lot at science fiction conventions.
Okay. Do you see a greater interest in science by younger people, and do you think any of that is a result of fantasy or science fiction entertainment?
So there's a two-part answer to that. So if I just take the first part of your question, do you see a greater interest in science by younger people? My immediate reaction to that is no, I don't see that, and one of the things that worries me so much is that I feel like I see our society in the United States as really trending in the opposite direction, in an anti-science direction, and that worries me quite a bit. But now getting to the second part of it, I think that the search for life elsewhere in the universe is the exception to that rule. People that I talk to, I've only been doing this type of work for a couple of years now, and whenever I tell people that I'm doing this, their eyes just light up, and everybody's excited by it. Everybody wants to hear about it. Just last week, I gave a little informal talk to some summer interns who were at my place for the summer, and they've been being exposed to research on climate change, and so I was asked by and a group of other students who came to visit the Goddard Institute for Space Studies that had been brought there by Andy Redknapp, an environmental writer who used to write for the New York Times and now does a blog for the New York Times called .Earth. And he brought some students there who were also thinking about spending summer thinking about Earth climate change and the impacts of climate change and so on and so forth. And so I was asked to give a little informal talk to them, and I was asked to not just talk about the science, but talk about my career and how I got to where I am today. So I told them some of the same stuff that I told you earlier in the conversation. But I also told them about what's been happening in the last few years, and then I'm working on this exoplanet stuff right now. And even though I was there talking to them about climate change, they still wanted to know about the exoplanet stuff too, even though that wasn't the topic and that wasn't what they were spending their summer doing. Anytime I mention it to people, they want to hear about it. The other thing, a couple other things I'll tell you is, and so I think that this idea of life elsewhere in the universe, most of which has been sustained through our lives by science fiction, has conditioned people to be fascinated by that idea, even if it becomes reality that people might try to rethink whether they're excited or afraid by it. Discovering life elsewhere, but still, I think people have been conditioned just to have that somewhere, in their heads, and so when they hear that people are actually working on it, it really interests them. The the other thing I was going to tell you is that since I have, during my career, been in different areas of science, mostly these different areas of science are populated by different scientists. So if I go to a climate change meeting, I'm seeing a different group of people for the most part than if I go to an exoplanet meeting.
Mm-hmm.
Okay, it's not completely different. There's a little bit of overlap. People like me and a few other people, but mostly they're different communities of people. And one of the things I've noticed is the difference in the demographics and the difference in the attitudes. The people who do Earth climate science for a living, some of them might be interested in science fiction, and a lot of them have no interest in science fiction. People who do exoplanet science are almost always science fiction fans. And one of the ways that I realized that is that when I go to these meetings, I'm watching other people and listening to other people give their talks. And I noticed that exoplanet scientists love to throw in sci-fi references during their during their otherwise completely serious scientific talks. They'll throw in sci-fi references. Sometimes it's just for fun, but they know that the audience that they're speaking to, and they know that they're speaking to an audience that appreciates science fiction, but also sometimes to convey a real idea. And so, for example, like we were talking earlier about the idea of a planet that's more habitable versus less habitable.
Mm-hmm.
All right, and the idea of a more habitable planet being one that would support kind of lush vegetation over much of the planet's surface, or more of the planet's surface than Earth does, and a less habitable planet would be one that's more like the Sahara Desert. All right, and so after I gave a talk a couple of weeks ago in Seattle, partly about that subject, and to introduce that talk, I had a slide with a picture of Arrakis from Dune,
Yeah.
which by the way is a very realistic portrayal of what an inhabited desert planet might be like.
Mm-hmm.
Forgetting about the sandworms. I don't know if there's any serious scientific theory for sandworms or for spice or any of that. but if you know about Arrakis, most of the planet is a desert, but there's water up at the poles, and that's where people can live and get the water that they need to sustain life. And in fact, it's been shown with studies with climate models that if you had a desert planet with just a little bit of water on it, that is exactly where the little bit of water on the planet would wind up accumulating in the polar regions of both planets. So Arrakis is a great example of at some level of scientifically accurate planet. Nonetheless, the point I was making is that as interesting as Arrakis is, it's a planet that if it were 50 light years away from the Earth and you were trying to detect the life that was there, unless the sandworms put tons of greenhouse gases into the atmosphere or something like that, you'd have a hard time figuring out that there was life there because the life was concentrated in two very small regions at the poles. But that is an example of the opposite. I had a picture showing the forest moon of Endor from the Star Trek movie, and that's an example of just the opposite. That's a planet that is more or less completely covered by vegetation. Actually, I haven't figured out a way that we can do that, but there are ways you can make a lot more of a planet covered with lush vegetation than the Earth is. And so I put those things into the talk because I knew they would immediately resonate
Mm-hmm.
with people, and in fact, when the person whose laptop I was putting my talk onto was cycling through my slides to make sure that they were okay and that they projected okay, he encountered that slide. He stopped and he said, "Well, that's great." And this is what you get from people in our field. They're all science fiction fans, and we're using it not for fun, but also to convey real ideas. And that's the thing. These things from science fiction are cultural touch points
Mm-hmm.
for most of the people in this field. And the other thing that you should know about exoplanet science that I've really noticed is that this is a field that is really dominated by young people, much more so other fields. Tremendous number of young scientists in the field of exoplanets, and I have to think that is not an accident. There are so many different areas of science that a young person who's interested in science can go into. Why are there so many young people in the field of exoplanets? And I can't help but believe that there's a connection between that and the fact that these are people who were raised with science fiction, who became enamored of the ideas expressed in science fiction, and now they see an opportunity to sort of make that come to life in their own career, and they do it. And so, in that sense, I think that science fiction is playing a really important role for certain segments of people in our society that is causing them. It's affecting how they look at the world, how they think about things, and is creating maybe a love for science in them that might not be there otherwise.
Mm-hmm. Okay. So just to go back to the science work, what have been some of the most exciting discoveries you've made in your career?
Well, okay, so I tried to think of a couple of things that I've done that I think were important, and maybe they won't sound important to someone who's not a scientist, but one of the first things I studied in my career is Venus, and Venus is sort of an interesting place. When astronomers first observed Venus through telescopes from the Earth, they could tell that it looked like it was rotating once every 4 days, because there are cloud patterns that you can track, and they would see that the cloud patterns would repeat every 4 days, and they figured that, so Venus must have a day that's 4 times longer than the Earth's day. And then we said, and then we got to the point where the science of radar had been developed enough so that from the ground people could bounce radar signals off the surface of Venus and have them come back to the Earth, which is amazing if you can do that from that far away.
Mm-hmm.
But they could. And the thing about radar is that it penetrates the clouds and goes all the way down to the ground. And when they did that, they realized that the surface of Venus was actually going around once every 243 days. And so apparently the atmosphere was spinning around 60 times as fast as the planet itself did, which shocked everyone. And people have been wondering for a long time how that possibly happened, that an atmosphere can spin around so much faster than the planet does. And so I did some work in the 1990s that I think showed how that could actually happen in an atmosphere, and why that would be a real thing, and what the physical processes are that would do that. And I think the big paper I wrote on it was in 1993, and I think that paper has more or less stood the test of time as a valid explanation for why this happens on planets that otherwise rotate slowly. So that's maybe one thing that I think I'm proud of in my career.
Mm-hmm.
On the Earth climate side, some people have wondered ever since climate change became a concern whether clouds might save us from climate change, and the idea is that as the Earth warms up, you would evaporate more water from the oceans. And people said, well, if you evaporate more water from the oceans as the climate warms up, then you're going to form more clouds, and if you form more clouds are bright, they reflect sunlight, so they'll reflect more sunlight, and that'll keep the Earth from warming up so much. And I did some research to show that at least over most of the Earth, that's probably not what happens,
Mm-hmm.
because while more water may evaporate as the climate warms up, the atmosphere is warmer too, and so it's harder to make a cloud, and so what winds up happening is probably that the clouds get thinner rather than thicker instead. And over most of the Earth, I think we're finding out today, that's an ongoing area of research, but I think we're finding out today that for most of the planet, that's true. So I was pleased with that piece of research, and I'm happy with the stuff that we've done recently that I've already described to you, that we're using our climate model to figure out which types of planets might be more habitable than other kinds of planets, and more detectable than life might be more detectable than other kinds of planets, when you start in a new field, you're always asking yourself, how can I make a contribution to a field that people have been working in for 20 years already?
Mm-hmm.
And you're always looking, where's my niche? Where can I tell them something that they don't already know? It's a little bit of an intimidating thing when you start to work in any new area like that.
Right.
And so this is something that we've come up with that I think is going to be an important thing, and I think it's going to be a useful thing to ultimately to NASA in deciding which planets should we spend more time analyzing and so on. So I've been pleased with that research also.
Okay. All right. So any last comments or points you'd like to make regarding anything we've touched on, or whatever else might interest kids, teens, and adults interested in science or science fiction and fantasy?
Mm-hmm. So first, on the reality side, I'd like the people who visit your site to know that NASA has a couple of exciting new missions coming up in the next couple of years. Next year, they're going to launch a satellite called the Transiting Exoplanet Survey Satellite, TESS.
Mm-hmm.
And then the year after that, in 2018, NASA is going to launch the James Webb Space Telescope. And part of what James Webb is going to do is to look for exoplanets as well, and so TESS is going to try to find exoplanets and to come up with good candidates for the next mission, James Webb Space Telescope, to try to analyze in more detail. And James Webb will try to then analyze those planets and learn something more about what their atmospheres are made out of. And so those two missions are going to be coming up, one in a year from now and one in 2 years from now. And so the exoplanet community is really excited about this stuff, and I think people who are interested in this are going to hear about a lot of really fascinating new discoveries that are going to come up in the very near future, meaning in the next 2 to 3 to 4 years. That we don't have to wait decades or centuries to be learning more about exoplanets. So I hope people, there'll be websites that you can go to. There'll definitely be Twitter feeds from the people who are interested in exoplanets should get on those Twitter feeds and get updates from them whenever possible. I think they'll learn a lot of neat stuff. The program that I'm involved in, we have a blogger. We have a blogger, a guy by the name of Mark Kaufman, who used to write for the Washington Post.
Mm-hmm.
So he's not a scientist, he's a layman, but a layman who's been interested in science and life elsewhere for a long time, and he's writing a blog for us that's called Many Worlds, and the website for that is Many Worlds, one word, no spaces, MANYWORLDS.space, and he puts out a column, a blog piece every week, not regularly the same day, but about once a week or so. He puts out a blog piece on some new aspect of the search for life and exoplanets, and again, he's a layman, so he's writing in English, unlike scientists who sometimes write in a way that's kind of inscrutable to the average person. He's writing in a way that people can understand. So people who are interested in the search for life elsewhere and what scientists are doing and what new things are being learned, I would invite them to go visit that blog and to read about what he's reporting on, because it's really interesting. And by the way, for fun, the NASA Jet Propulsion Laboratory has these posters that people can get. The Jet Propulsion Laboratory, JPL, has what they call the Exoplanet Travel Bureau.
Mm-hmm.
And what they are travel posters like you might have imagined seeing in a travel agency years ago, only instead of travel posters inviting you to go to Aruba or someplace like that, they're travel posters for exoplanets that imagine what it might be like if you visited those exoplanets. And people can go to the JPL Exoplanet Travel Bureau and just download these things and print them out on poster-sized paper if you want something neat to hang in your room.
Mm-hmm.
But then, on the science fiction end of things, the message I want to emphasize is that nature is always more imaginative than we human beings are, and the lessons from that always at least one step beyond what we scientists can imagine. And it plays this crucial role, I think, in our society and in scientific society. It's an important part of pushing ourselves to think about what's possible. And the artistic license that science fiction writers have, allows them to go to places that scientists are afraid to go because they don't think it conforms to what they believe are the physical laws of nature and how those physical laws play out in certain settings. And we learn over and over again that our understanding of these physical laws is more limited than we realize. And so science fiction plays such an important role in helping us think beyond what we normally think of. And that's why I think that there's a real synergy between science fiction and science research that is maybe healthier now than it's ever been before, and I think it's going to become only healthier in the future as this field becomes more and more expensive and exciting to us.
Okay. All right. Well, I really appreciate your time. That was great. That was really interesting.
Oh, I really appreciate speaking to you.
Please visit chrisalvarez.com for more cool stuff. That's CRISALVAREZ.com. Thanks for listening, and keep imagining the future.